We are now recording. Now let me, I thought I had this set up for current slide. It got off of it. Okay, I'm going to get my pen set up. Okay. Let me hit just a couple of things first. I said this at the beginning of last class, so I don't think you were in here yet, but I think I said it Monday too. Still working at trying to get Blackboard set up. I had some difficulties over the weekend because the Blackboard went down. And then I've had no time during office hours Friday, or I didn't have much time. I had time to get one class pretty much set up on Monday afternoon during my 2 hours, but I had so many other things come up I couldn't get but most of one class done. I went home that night and got the rest of it done. But that's all I had time for because the computer I was using at home, I leave this computer in here for Dr. Bryant to use in his physics classes, and so I was having to use a laptop we had at home. It had that sorry Windows Vista operating system, and it does not interact well with Blackboard at all, so it was really slow and difficult to get done, and it ultimately the battery died before I could get more than one class done, so I didn't want to wait for the battery to recharge, so I hung it up and quit. Okay, but anyway, I'll try to get that done. I also have received my first couple of papers for the term. I've got one of those graded already. I've got another one to go. And my physical science class, because it's a mini-term, we've already done one lab and one test, so I've already got grading to do. And we got, I think, 20 people in that class, so that's a lot of labs and a lot of tests to grade. So it'll take me today and probably Friday and maybe even the weekend to get caught up. But hopefully I can get it done sometime in that time frame. All right, good deal. Any questions on anything we've done so far? Okay. If not, here is, we left off on Chapter 1, Introduction to Differential Equations, 1.1, Definitions and Terminology. Wow. These examples take a while. And we're on page 9, example 8b. Okay? Two-parameter system. Y is equal to C1e to the x, and this is Treddy back, okay, plus C2xe to the x, okay. That's an explicit solution of the linear second-order differential equation y double prime minus 2y prime plus y equals 0. Okay? Now, it says to verify that. How do we go about verifying that that solution does satisfy that equation? What would you do? What would be some of the steps you take to verify that solution satisfies that differential equation?
You'll plug in the solution to the problem, something, or
okay, you will be plugging in, but you got to do a couple things first before you plug. Yeah, take a derivative. You got to figure out what y prime is. So let's do y prime. And what is y prime? Help me. It's the first derivative of C1e to the x.
if we take a derivative,
Take the derivative of y. Yeah, that's y prime. C1e to the x. Yes, okay. That's what's beautiful about exponential functions. They're the same. That's the first term. Second term. Oops, that's the product rule. So how do we do that? Second, okay. Let's write down the C2. That's just a constant. And what were you saying? Derivative of the second. So the first is the x, and what's the derivative of e to the x? E to the x, okay? Plus, and that's another C2, okay? Or we could have factored out the C2, it doesn't matter, huh? No. It's e to the x, because you take the derivative, okay. What we did here, we just took the C1 times the derivative of that, that's that. Plus C2 times this times the derivative of that, that's that one. Plus C2 times this times the derivative of that. The derivative of x is 1, so that's just C2 e to the x. Okay, so there's your first derivative. Let's do the second derivative. Y double prime. First term, C1 e to the x, okay? Plus, okay, x e to the x plus C2 e to the x plus C2 e to the x. Oops. All right. Now we can combine these two and just make it 2C2 e to the x. Is that okay? Yeah. All right. So let's delete that second one. All right. Now we plug in. Y double prime is C1 e to the x plus C2 x e to the x plus 2C2 e to the x. Got it. Minus 2 times y double prime, y prime. So can we do that all in one step? That'd be minus 2C1 e to the x, right? Right? Minus 2C2 e to the x, right? Plus, minus 2C2 e to the x. Oops, this has the x in it, okay. X e to the x, I'll left that out. Okay? Plus y. Well, y is up here at the top, okay? C1 e to the x plus C2 x e to the x. That's an x. All right. Supposedly, that's equal to 0. Is it? Well, here we have a C1 e to the x. Here we have a C1 e to the x. That makes 2C1 e to the x minus 2C1 e to the x. That adds to 0. Right? Here we have a C2 e to the x. There we have a C2 e to the x. Add those together to get 2C2 e to the x minus 2C2 e to the x. Sure enough, those three go out. Add to 0. And here we have a 2C2 e to the x minus 2C2 e to the x. Sure enough, 0 is equal to 0. That did it. All right, we verified it. All right. Now, what do those look like? What's that? No, what do does that look like? The y look like?
The solution
the two-parameter system, that two-parameter equation look like? Okay? You pick different values and go with it. In figure 114, we have shown 7 of the double infinity solutions in the family. The solution curves in red, green, and blue the graphs of particular solutions. Y is equal to 5e to the x. That would be if C1 was 0 and C2 was 5. That's the red one. Okay? So, when C1 is 0 and C2 is 5, that's this red curve here. Okay? This one right here. Going to infinity like this. It comes in, decreases, has a minimum, and then shoots up and goes up pretty quickly. Okay? Now, the I've lost it. Green one is 3e to the x. Okay, so in this case, C1 is 3 and C2 is 0. And this is the string curve here. It just is a 3e to the x. So that just is going up like that. Okay, that's simple exponential function. Okay, and then the blue one is is a combination of those two. Okay, that's with y is equal to 5e to the x, and C1 is 5, and C2 is minus 2. No, it's not quite the same. I'm sorry, I got crossed up. 5e to the x minus 2xe to the x. So that's not those two. So that's the blue curve. So that goes up like this and then heads down. Because this one is a minus 2xe to the x. That one is up overpowered the other, so it winds up going down. Now, are you expecting to do these graphs? Nah. Okay. But if you have hold of a graphing calculator that will do them, you can look at it. Okay. Or you can, if you have one of those computer algebra systems or one of those things, you can do that. Now, sometimes a differential equation possesses a solution that is not a member of one of the family of curves. Okay? It just happens to have another. Okay? That is a solution that cannot be obtained by specializing any of the parameters in the system equation. Such an extra solution is called a singular solution. It works, but it doesn't fit the pattern of the others. Okay? And
excuse me. What do you mean you don't fit the patterns of the others?
okay, like if there was a solution that solved this differential equation but didn't fit that pattern, I'll give you one. Okay? Y is equal to 0. Okay? Well, yeah, that would be C1 is equal to 0 and C2 is equal to 0. So that would fit. But so you could do that. But Y is equal to 0. Y prime would be 0. Y double prime would be 0. So yeah, that would be that would fit this differential equation. But it does have a pattern there. If there was something else in there that it didn't fit, well, I thought that would work, but it doesn't. Then that's a singular solution. If you happen to notice, hey, and usually it's something simple like that. It's patently obvious. Y is equal to 0. Oh, now that fit these, but if you had a two-parameter system, but you could not get any way for Y to be 0, that would be a singular solution. It obviously solves the equation, but it doesn't fit the pattern of the rest of them. Okay. Now, example 9. Slightly different type of deal. Okay. This is supposed to be definition and terminology. I guess that whole purpose was to get the term singular solution out there. Here's a different thing. Here's a function. X is equal to C1 cosine 4t. Whoops. X equals C1 cosine 4t. And X is equal to C2 sine of 4t. Okay, two different functions. C1 and C2 are arbitrary constants or parameters. Put any value you want to. They're both solutions for of the linear differential equation x double prime plus 16x is equal to 0. Okay? Now, do we need to verify that? Just to make sure that's correct? What would we have to do? Yeah, x prime of this one would be?
C. I'm having a hard time seeing. Okay, it's just gonna be C1.
C1's certainly going to be there. Say again?
It's my negative.
It's going to be negative.
Negative. $14. Yeah.
Oh, yeah, but 4.
Oh, 4.
Yes, sir.
I'm sorry. I'm looking for a physics class. It said 257.
Okay. It said it started at 2:30, right? Or something like that? Okay. The 2:30 to 3:30 is the lab period. And he usually assigns that to you the day before. They're online labs. So you don't have to actually physically be here to do those. So I take it you were in class earlier. Okay. The regular class starts at 3:30. The lab was at 2:30. Okay. So yeah, you can go over there and wait. They will be moved to he's moved them to this class so he can use my computer and doesn't have to check one out of the library. So
Thank you.
yeah, you can go there and do whatever you want to do for the next close to an hour. But at 3:30 you'll be coming in here. I'm sorry.
Sorry for interrupting.
No problem.
I appreciate it.
Hey, I have a meeting to go to.
That's too bad. No, I'm joking. Okay. Okay, this will all be recorded and out there on YouTube. All right. Okay. Are you going to finish what he started? X prime would be minus 4c1 sine of 4t. Let's go on and do the x double prime for that one too. What would that be? You keep the minus, and you'll keep the 4, but then you'll have another 4 to multiply through it from the chain rule again. So it'll be minus 16. C1, C1. Cosine. Okay. The minus that was there stays there. Okay. Derivative of sine is cosine. But it was minus in front, so it stays in front. So it's minus 16 C1 cosine 4t. Let's do the other one too. X prime here would be 4 C2 cosine 4t, right? And x double prime here would be, second?
16.
Okay, it certainly will have a 16. C2, it'll certainly have that.
Sorry.
Will be a sine 4t, but it's going to be a minus because the derivative of cosine is minus sine. And sure enough then, if you look at both of those, x double prime, this one, minus 16 c1 cosine 4t plus 16 c1 cosine 4t, that's equal to 0. And minus 16 c2 sine 4t plus c2, 16 c2 sine 4t, that adds to 0 too. So both of those satisfy that equation. Okay? Now, because each of them does, any linear combination of them, in other words, some of them does too. They're not saying that yet, but we will say it. Okay? All right. Finally, it's straightforward to verify that the linear combination of these two solutions is a two-parameter family. X equals, so your overall equation, rather than these two specific ones, would be x equal c1 cosine 4t plus c2 sine 4t. That's your general solution that works for all, not specific one to the other. Any linear combination of those. It's also a solution for the differential equation. And you can take that and take the first derivative, second derivative, and you'll get the same terms you did before and see it still works. Okay. Now, this one's sort of a pain in the neck. I almost hate to waste the time to do it, but maybe you'll need to do this or see it before. The one parameter family of quartic monomial function y equals c x to the fourth. Oops. Is an explicit solution for the first order equation xy prime minus 4y equals 0. Okay? Let's verify that. What would we do first? Find the derivative. Equal to c x to the cubed. Exactly. So that's your y prime. So we're saying x times 4cx cubed minus 4 times c x to the fourth, that's your y, is that equal to 0? Well, sure enough it is. This would be 4c x fourth minus 4c x fourth, and sure enough that is always identically equal to 0. Okay? It says that's is an explicit solution on the interval of negative infinity to infinity. Now, I don't want to have to draw these, but if you did draw them, y is equal to cx to the fourth. It's not that hard. If c is positive, let's just keep it simple, positive 1, it does something like this. It's kind of like a parabola, but it's steeper on the sides and flatter in the middle, right? But if that was a minus 1, if c was a minus 1, then it would be, what color would you like? Second?
Blue.
Blue. Light blue, dark blue. Pick one.
White.
Light blue. Okay. It would be like this. Okay? So those would be two possible solutions. One would be equal positive 1, one would see equal negative. Okay? Now, this just happens also to be. What if we started here and use negative 1 there up to here, but then change the positive 1 up to there? That would still be a solution. Or if we started with positive 1 here and at 0 change the negative 1, that would still be a solution. They would be piecewise solutions because they're different functions, but because they intersect there at 1, at x equals 0, y is equals 0, you could exchange there and tag team and go with the other route. And that's what they're talking about here. So here's another possible solution. Okay, let me go back to black. And another solution would be y is equal to piecewise defined function negative x to the fourth anytime x is less than 0 and positive x to the fourth anytime x is greater than 0. Now you probably technically ought to put an equal sign under one of those, but it really doesn't matter. But you really should have it so it's equal to 0 too. And it doesn't matter here or here because it's the same value at either one of those. So that would be the one that starts here when x is less than 0 and follows this curve, and then picks up the second one and follows up there for the positive x. Okay. So you could have a piecewise defined function, and in the book they show this being the equal here. They didn't show it in the verbiage, but they showed it in the figure. Okay. Now, we're not going to dwell on this, but they do mention it here, systems of ordinary differential equations. Up to this point, we've been discussing single differential equations containing one unknown function. But often in theory, as well as in many applications, we must deal with systems of differential equations, and that would be systems of differential equation with two or more equations involved, involving derivatives of two or more unknown functions of a single independent variable. For instance, if x and y denote dependent variables and t denotes the independent variable, then the system of the first order differential equations d by dt, dx by dt is equal to f of t xy, and d by dt, dy dt is equal to some different function g of t, x, and y. Sorry. A solution of the system such as that is a pair of differential functions, x equal phi1 of t and x equal phi2 of t, defined by the common interval I that satisfies each equation. That's all they say about it. Without saying any more, you can't really do too much with it, so we'll leave that alone. They have these remarks at the end of each section, and I have before tried to go through these in sort of gory detail, and really it's more of an expenditure of time than it's worth. So if you have any questions about them, we'll do it. I will mention a couple things they have. Sometimes our functions that we have are not nice, pretty functions like a power function or a cosine function or something like that. Sometimes those functions are, sadly enough, but all too true, an integral defined function. For instance, f of x might be the integral from a to x g of t dt. Okay? Now, it may not be that you can write this explicitly as a function of x, but you can write it as an integral and use different values of x there, and you'll get different values. And when you do that, that's the integral. Okay? And that may be the only way you can express that function. Okay? Now, the fundamental theorem of calculus part 2 says you can take the derivative of this, L prime of x, which is d by dx of the integral from a to x of g of t dt, and that, you see, a derivative undoes an integral, so you wind up with g of x. Okay? So you might not be able to specify alpha of x directly. You only can write it as an integral, but you can specify its derivative directly, and that would be g of x from the fundamental theorem of calculus part 2. They also refer to some non-elementary integrals. That is, an integral of a function that does not have an elementary function antiderivative, and elementary functions include the familiar functions studied in typical pre-calculus course. These are the elementary functions, not non-elementary. Constant functions, polynomial functions, rational functions, exponential functions, logarithmic functions, trigonometric functions, inverse trigonometric functions. Those are all elementary functions. And I hate to say it, but almost everything else, maybe not everything else, is non-elementary. So, and then we've also talked about a general solution. If you have a parametric solution like we did before with C1, C2s in it or whatever, but then you might also have some specific function that will work, then the linear combination of those will be your general solution. Okay. That finally ends 1.1, which is supposed to be just derivative definitions and terminology, but there's quite a bit of calculation to do in it too. So homework exercises, do any of the odds 1 through 7, do 9, do 11 or 13 or both, 15 or 17 or both, 19, 21 or 23 or both, 25 or 27 or both, do 29, either 31 or 33 or both, do 35, either 37 or 39 or both, and try to do 41. Now the others are discussion problems. They don't have answers in the back, so you don't need to fiddle with those too much, but you might want to think through them. There is one on problem 51 that talks about the folia of Descartes. Okay? Now, I'm not saying you need to do anything with that, but that might lead you to a paper topic, and the paper topic could be, who was Descartes anyway? Or, what is this folia of Descartes, or how is it used? What fields of study is it applicable to? Or, how did, if you can find this information, how did Descartes, develop this folia of Descartes? Okay, so you could maybe see one or more paper topics in some of these questions. Okay, let's end that and move to 1.2. Okay? 1.2 is going to introduce the concept of an initial value problem. Okay? And they start out by making it about as complicated as you can get it. Okay? And here's what you'd have. On some interval I containing your x sub 0, whatever that happens to be, your initial value, the problem of solving an nth order differential equation subject to n side conditions specified at one point x sub 0. So this may have been your situation. Here you have d, the nth derivative of d, y, dxn. That's equal to some function of the variables x, y, y prime, dot, 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 all the way up to and including y to the n minus 1, I think. I can't, yeah. Y, the n minus first derivative of y. Okay? That's your differential equation. Okay? You have an nth order differential equation over here, and that's equal to some function of your independent variable x, your dependent variable y, the function y, and then all your derivatives of y up to the n minus first. Okay? Now if you notice there, this covers the n minus first one, so that goes, the nth one, that goes everything up to that. Okay? That's a very generic way of expressing it, but that covers all possibilities you have. Okay? But here's the new part. You want this subject to this. These are called your initial conditions. That y at this initial value x0 is equal to some y0. Okay? y prime at x equal x of 0 is equal to some is equal to some they're just calling that y1, y double prime evaluated again at x equals 0, x sub 0, and that's equal to some y2, and dot dot dot, continue these all up into y, the n minus first derivative of y, is equal, evaluated at that same value, x sub 0, and that's equal to some y sub n minus 1. Why they started with it so complicated, seems like they could have given a few simpler examples and then expanded to this, but this covers it all the possibilities here. That was hard to read.
The first one is that
y0. Y evaluated at some value for x, we're calling that x0, and then all your derivatives are going to be evaluated at that same value, x of 0, but they could have different values. So y at x0 is going to be y0, and y prime at x0 is going to be y1. Y double prime at x0 is going to be y2, and y triple prime at y3, and y, the n minus first derivative of y, is going to be some y sub n minus 1. Some value, but they're all evaluated at x0. That's your initial value. Now, why do they call it initial value? I'm not really sure. You tend to choose that first value that's defined for. That, to me, would make sense for initial value. But it could be defined anywhere here. You just pick that value right there, but then you do all your derivatives at that value. It doesn't have to be the first value. That's usually what you connote by that, but it doesn't have to be. All right. So the y0, y1, up to yn minus 1 are arbitrary constants, just some value. Goodness, my throat runs out about this time of day. It is so dry. We go to 3:15. Let me do a quick pause here and just get something to wet my whistle. I got something. All right, so this is the generic form, as soon as it comes on, of an nth order differential equation that's an initial value problem. Initial value meaning it's some given value for x, you know the function value and each of the derivatives value up to the nth derivative. Now, you can think of this as having n independent variables. 1, 2, 3, 4, 5, 6. Notice 1, 2, 3. So this is the first derivative is the third value. Third independent value. So the n minus 1 would be the n plus 1 value. So it actually has n plus 1 independent values there, and you've got n plus 1 initial equations. because here you have 1, 2, 3, 4. You have n. You just have n. So this is your n plus first one. Okay, so you can think of it that way. These are called your initial conditions. Okay? The differential equation is your nth order initial value problem, IVP, and the second line indicate your initial conditions at that one single value x of 0. So here's a geometric interpretation, and I'm probably not going to draw it for you, but let's just keep it simple, okay? dy dx, just first derivative, dy dx is equal to some function of x and y. You only go up to, if that's an n, you go to n minus 1. If this is a 1 here, you go to y to the 0, which is just y. Okay. The 0th derivative of y, which is just the function itself. So you have a two variable thing there. It's subject to one initial condition. Y at x0 is equal to some y0. Okay. That's when your nth derivative is the first derivative. That would be an initial value problem. Okay? And that's called a first order initial value problem. Now, let's say that you get a family of solutions, family of curves here. Whatever it happens to be. It could be like that, like that, like this, like this, like that. Whatever. Those are the possible solutions. But when x is equal to 0, y is equal to 0. Well, here's your x0 on the x-axis here. There's x0. There's your y0. That tells you it's that curve right there, none of the others. So before you had a family of solutions. Now you have that one solution because your initial condition named it. It nailed it right there. Okay. Now, it's kind of like, in a little bit of way, when you had an indefinite integral, right? You did the integration, found the antiderivative, and then you wrote it down plus c. You just didn't know what the c was. But if they gave you an initial condition that when x equals this, y is equal to that, and you had a solution, y is equal to cosine 3x plus c. And they gave you x equals something, y is equal to something. Plug in the x, you know that y's got to be that. Evaluate the sine of 3x here, and any difference in that, that's what your c is. And that nailed it down. That said it's that curve, not this curve or that curve or anything. It's this one right here. Same thing here. Okay? Here's a second order differential equation. d2y dx squared is equal to some f of x, y. Now you can go up to y prime, okay? Because your second derivative is on the left-hand side. The right-hand side can go anywhere up to y prime. Here you're going to need two initial conditions. X at y at x0 is equal to some y0, and y prime, at x0 is going to equal some y1. Some different or same value. It doesn't have to be the same value. Okay? Now what does that mean? Well, here you have a family of solutions for this one. Okay? All these solutions, and they had would have normally had two parameter curves. One of them, you narrow it down by x0 is equal to x0, y0 has to be on it from here, but also that the slope of the tangent line at x0 has to be y1. So that gave you here. You may have had several curves that pass through that point. Then you narrow it down to the one that has that curve, that slope at that point as well. Okay? I don't think their illustration was as clear as it could have been. All right? Those are just called your initial conditions. So let's see if we can do something with that. In the problem set that I just assigned, you would ask you to deduce that y is equal to c e to the x. Let's clear this. Yuck. Yeah, this is it. My throat was feeling better. Now it's sort of clogging up again. So here we have asked to deduce that y is equal to c e to the x, okay, is a one-parameter family of solutions to the simple first-order differential equation y prime is equal to y. Okay? Think that's the solution? Let's see if it is. What would you do first? Yeah, find the root of y prime would be c e to the x. And sure enough, y prime is equal to y, isn't it? So yeah, that is a solution for that differential equation. Okay? Now, you could have an infinite number of those, by the way. Okay? Different c's do different things for you. Okay? But let's say we have an initial condition. Let's say, and basically that's good for all real number vectors. That's always true. Okay, from minus infinity to infinity. Let's impose an initial condition saying that when x equals 0, y is equal to 3. So when x is equal to 0, y is equal to 3. Your x0 here is 0, your y0 is 3. Okay? Well, let's plug it in. Okay? So y is equal to c e to the x. We want 3 to equal c e to the 0. Right? Plug in 0 for x and 3 for y. Okay? Well, what is e to the 0? 1, yes. So if e to the 0 is 1, this requires that c is equal to 3, right? Because if this is equal to 1, then 3 is equal to c, okay? C times 1 is c, right? All right. Now, y is equal to c e to the x. Get back here. Okay. When c is equal to 1, that would be y is equal to e to the x. That would be the curve that goes through there. Y is equal to 2 would go through here. Y is equal to 3. C is equal to 3, that would go through there. C is equal to 4 will go even higher. C is equal to minus 1 will go through that one. C equal to minus 2 down here, minus 3 here, minus 1/10 here. You have a whole family of curves there, but the one where 0, 3 is on that curve is that one right there. That one right there, that is your solution curve. If you have that initial condition, initial value, that's what you have. Okay, that's all. Okay, now the B part. Now if we demand that the solution curve pass through the point 1, -2, in other words, we say we want the curve that goes through 1, -2, that's saying when y of 1 is equal to -2. When x is 1, y is -2. Well, let's go back to our formula, our solution. Y is equal to c e to the x, right? Plug in these values. Y is equal to -2 is equal to c e to the 1. Well, let's divide both sides by e to the 1. C is equal to minus 2 over E. Now, if you got a calculator, punch that in. See what you get. Oh, you don't have a calculator? Okay, it's all right. That's what your C would be. Rather bizarre number, but that's what it would be. And number 1, C would be negative, so this function is going downhill because y is equal to some negative e to the x. E to the x is always positive, y is going to be always negative, and it passes through the point 1, negative 2. And it's that curve right there, and then your C to make that curve happen would be that weird number there, negative 2 divided by e. Okay? So that's what your initial value problem does. Rather than have a family of curves, it picks the curve that fits those conditions. One and only one curve. Okay. Now, both of the ones we've talked about so far said these are good for all real numbers x. It's not always going to be the case. Okay? We haven't done exercise set 2.2 yet, so why are they doing that? You will be asked to show that a one-parameter family of first-order differential equations. I'm going to clear this screen. Here's your differential equation. Y prime plus 2xy squared is equal to 0. Time out just a moment here. Tell me something about that differential equation. What are some of the classifications of it? It's an ordinary differential equation. It doesn't have partials. Those are first derivatives, right? Second, what's its order? First order. Okay, the other thing that we do is it linear or nonlinear? Nonlinear, because that y is squared. If that had been plus 2x squared y, that would be linear. But with that being y squared, nonlinear. Okay, if it had been y prime, nonlinear. If it had been y prime plus 2x y to the 1/2, not linear. Okay. In order to be linear, all the y's and y primes have to be order 1, not derivative order 1, but, raised to the power 1, and no cross products, no y times y double prime or y double prime times. You can't have any of those. That would be a nonlinear. We haven't run into many of them, but that's why I wanted to point it out. Okay? It says here, it says to show that this equation, that the one-parameter family of curves is this. So here they're saying a solution. Y is equal to 1 over x squared plus c. Okay? They're saying that's the solution set, single parameter c. Okay? Do you feel like verifying that? It's really not so awful to do. The first thing I would do, I think the first thing I would do is write it this way. X squared plus c to the minus 1. And then the next thing to do is take a derivative. Y prime would equal to minus x squared plus c to the minus 2 times 2x. So rewriting that would be minus 2x over x squared plus c squared. Yeah. Okay? So that's our y prime. So let's plug that in here. Minus 2x over x squared plus c squared plus 2x times y squared, well this is y squared, 1 minus x squared plus c squared. Is that equal to 0? Well, sure it is. Because this is going to be a minus 2 over this thing. When you square that, you get 1 over x squared plus c squared. And minus 2 times that plus 2 times that is going to be 0. So sure enough, that works. And it wasn't that hard to verify. Okay? Might be hard to graph, but not hard to verify. Okay? If we impose the initial condition y of 0 equal negative 1, y of 0, I'm sorry, y of 0 equal to negative 1. Why do I have a comma in there? Okay. Y of 0 equal negative 1. That's a initial condition. Or is it? Okay. Let's see what happens if we put x equals 0. We'd have y equal 1 over 0 squared would be 0, so that would be c is equal to negative 1. So obviously c must be negative 1, right? You see that? You put a 0 in for x, that gives you 1 over c, and that's equal to y, but y is going to be minus 1. So multiply both sides by c, divide by minus 1, you get c is equal to minus 1. 1 over minus 1. Okay? Now, if you were to graph this this function here, oh yeah, then if you plug that in here, okay, that's what I was going to do next. So this would give you y is equal to 1 over x squared minus 1, right? That would be when c is equal to minus 1. Well, hopefully you can look at that and say, guess what? X can't be plus or minus 1, right? Because that would make your denominator 0. So basically that's going to be a family of curves that you have a vertical asymptote x equal minus 1 and positive 1. And then we know that when x equals 0, y is equal to 1, or negative 1, so it's down here. So it's going to be like this, and then this is going to be like this. And that's what they showed in the text here. That's your family of curves. With different c's, that would be different values. But when c is equal to, if x is going through 0, negative 1, it must be that curve right there. Okay. Now, you can't say to this one, this is good for all values of x. It's not. The others are saying, oh, this is good from negative infinity to positive infinity. This one is not. If you put that c of negative 1 in there, then you get this. This is not defined for x equal plus or minus 1. Good everywhere else, but not at those two values. So sometimes the choice of your initial point might make a parameter choice such that you have to, your domain changes. Okay, and this one would be that. Okay. Now, what's more, since you chose 0, 1 to be on that curve. 0, 1 is on this curve. It's not on this curve. It's only on this one. So now you're not just limited to not allowing plus or minus 1. You now have to stay between minus 1 and 1. Can't equal either one. So the interval on which this makes sense is from minus 1 to 1. Not minus infinity to infinity, minus infinity to 1, and then 1 to minus negative 1 to positive 1, and then anything. You can't do that. You're limited to that part right there because that has to be on the curve. It's not on that curve. It's not on this curve. It's on this one. Even though this solution would allow these, the curve does not have that. So you're limited just to that portion there. It's just sort of a minor point, but it could be meaningful. Okay. You can't say it's good everywhere because you cannot ever be plus or minus 1. But that then excludes that you can be over here or over there because the 0, 1, 0, negative 1 is not on either of those means. So you can't do it. All right, I think we've run out of time. Sorry about that. We're going to start next time with example 3. Homework exercises here. I think you can do number 1. I think you can do 3 or 5, which is basically just like the one we just did, only different initial value points. Okay? And then hold off the others until we get to get some more done. Okay? So we'll begin next time with example 3. Okay? All right, good deal. And were you in here when we talked about it? I've been telling all my other classes, have a good weekend, see you Monday. I won't see you Monday, okay? Because Monday is Labor Day. I couldn't remember if Labor Day was, if Monday was the first Monday in September or the last Monday in August. But no, it can't be the last Monday in August because that ends Saturday. So we don't have class on Monday. Sorry about that. Get over it. Okay. Next Wednesday.